I have been 6 years in Singapore and just last September returned to the United States, and now I'm a visiting scholar at Arizona State University. So just to get right into it, I want to talk to you about a watershed. And it's a watershed in ways that I think it's kind of new. It's not like the parallel processing watershed or the development of VLSI, but it's a watershed. I mean it in terms of an event or period marking a turning point in the course of action or state of affairs. It is underway right now. Here's my thesis. For 50 years, floating point operations per second have been the currency of HPC performance. Flops. So, well, I think that's changing, whether we realize it or not. The end of Moore's law and the rise of AI, all the machine learning activity, have made us realize that IEEE floating point is really long in the tooth. It's long overdue for replacement. It was based on the design rules of almost 40 years ago. This is a watershed. It's a revolution and it's well underway. And I think it's going to be less painful than the conversion from serial to parallel. Just a meme for you, a series of memes. Computers in 1985, computers now, 1,000 times smaller, 1,000 times faster, a million-fold improvement in Moore's law. This is what arithmetic looked like in 1985, IEEE standard. This is what it looks like now. I think you get my point. I call IEEE standard floats weapons of math destruction. They really were designed for the 1980s engineering limitations when, well, transistors were very expensive and communication was regarded as free. You cannot guarantee repeatable or portable behavior. Even to this day, the IEEE standard has not been able to achieve this. Computations change when parallelized. We want everyone to be able to use multi-core, massively parallel ensembles. Parallel processing is the rule of the day, but what happens when you program something to run in parallel and it gets a different answer? You don't know whether it's because of rounding errors, because of lack of associativity, that is, or because you did something wrong when you parallelized it. That's a really big hit on programmer productivity. When your 32-bit accuracy isn't just not quite enough, it forces you to go all the way up to 64-bit. For a lot of applications, 32-bit is almost enough, but not quite. It's also illogical. X is not equal to itself. A NaN value is not equal to a NaN. A equals B doesn't mean a function of A is equal to a function of B. That's really, really awful. I mean, 0 is supposed to be equal to -0, but 1 over 0 is infinity, and 1 over -0 is negative infinity. So that says infinity equals negative infinity. Poor handling of overflow, underflow, and not a number. Dynamic ranges are not well matched to application needs. You really need something about 10 to the minus 13th to 10 to the 13th for most applications, not what we've got now. These status flags where you raise a flag when there's inexact or overflow or so on, they're not supported by languages. So programmers don't see them. They only see the numbers that are produced. They don't see what the flag is unless they get out a debugger and single step all the way through their code. So everybody in HPC is out of bandwidth. It's been getting worse every year, the memory wall. If you use too much precision in your integers and your floats, you're wasting memory, bandwidth, energy, and power, and of course, time. Programmers use excess precision so they don't have to think, or because the optimal precision is not native to the hardware. Maybe they don't know what the range of an index is going to be, so they just use a whopping integer. But mostly they just use 64-bit precision everywhere. These current methods are coming from a time when operations were very expensive and moving data was practically free. The way I put it is in 1963, a transistor cost about as much as a tire for your car. So if you even wanted a flip-flop, you're gonna like buy a new set of tires. That's how expensive it was. 1963, that mentality was even pervasive by the time they were starting to form the IEEE standard. Overkill precision is a luxury we should consider doing without. And this is from everything from mobile devices like your cell phone for better battery life, or even exascale supercomputers where, at least for a while, they said you shouldn't use more than 20 megawatts. I think some are going over that now. What if we could get better answers with fewer bits? That's the watershed. I have a hobby of asking people, how do you know your answer is right when they're doing these great big scientific computations? And the usual reaction is laughter. And they say, well, what do you mean? They haven't even got any thought to it. That's actually the most common response. Or they say, we use double precision. Like that's a guarantee of the correct answers. Or it's the same answer we've always gotten. Or it's the same answers others get. Or I use tried and tested software. What could possibly go wrong? Things do go wrong. In another version of this talk, I give examples of the Ariane 5 missile blowing up and oil platforms collapsing to the bottom of the ocean. There's a raft of these things that can go wrong if you trust floating point too much. So IEEE 754 is a mess. This is just a little tiny view of the mess with a 16-bit example. It has 4 exception types, 2 different kinds of 0, 4 different rounding modes. And this is the nest that you have to go through, if the decision tree you have to go through just to decode a number. It's a lot of different cases. The dirty secret is that when all these companies that say they support IEEE 754 in hardware, well, they first check the exponent, and if it's all zeros or all ones, they trap to software or microcode, and they run the operation at about 200 clocks, way slower than the rated speed, which is based on all the floats being normal, bottom line here on this slide. So that's problematic in a number of ways. It leads people to using a flag on their compiler that says no EEE, because they get a lot better speed, they notice. It means you're going to get different answers on different systems, because some of them are using these exceptions and some of them have turned them off in order to make things go fast. So you don't have really a standard if you have an IEEE where people get different answers on different machines. Why care about reproducibility? We've gotten so numb to all the lack of reproducibility in floating point calculations that we just don't figure we have to live with it. But cloud computing is giving different results on each run, and that devalues the computations, makes us trust them less. Huge scale calculations make reproducibility harder to achieve than ever before. What used to be small, rare discrepancies can actually cause a butterfly effect and propagate to make a really big change. I'll give you an example of that in a few slides. Programmers then have to waste time figuring out why are the answers different? What is going wrong? So they waste a lot of time on that. Here's the example, climate prediction. These are different models, different versions of a model, and the colors are multiple runs of that model over and over again. They just with the same input data and the same program, they can vary by that much. And people say, well, that's just floating point drift. I'd say this is probably being caused by a lack of associativity in the additions. This is too politically charged to allow arguments, because people are always trying to denigrate climate prediction models because they say you can make a computer say anything you want. And when this kind of thing happens, it lends some weight to that argument. So same computer reproducibility. A lot of people are shocked by this. They think that, well, of course, if you run the same program on the same computer a few seconds apart, it will do the same thing. But we know this is not the case. If you set x equals 10 to the 160th in a double precision number, IEEE standard double precision number, and the computer then sets y equals x squared, so it's 10 to the 320th, computer does some other stuff for a few milliseconds, and then you calculate the square root of that, and you get back 10 to the 160th, like you'd like. Seconds later, same program, same data, you get z equals infinity. WTF. Programmer invokes the debugger and always gets infinity. So he tries putting in a print statement. And inserting print statements, the code you always get z equals 10 to the 160th. What's going on is that the compiler is using the 80-bit extended long extended register that's been in x86 processors since I guess they've been using it since the 8087 coprocessor was introduced in the 80s. And of course, that will overflow if you actually have to store it in a 64-bit number. It has a great big exponent. It can handle 10 to the 320th. But as soon as you, let's say, step through it with a debugger, then you're going to overflow because you're going to see that as a 64-bit number. Here's why linear algebra isn't portable with floats. All I have to do is show you a 4x4 matrix multiply, I think, to make you a little bit aware of how bad things can get. These are all single precision numbers. They're all exact in single precision. A dot product requires summing the pairwise 2 to the 54th, 2, -1, and -2 to the 54th. So let's use IEEE double precision to protect against rounding error. Parallelization changes the order of summation. It can. And there are 15 different ways to sum up 4 numbers. Do you feel lucky, punk? Well, here are the possible rounded values you get from that one element of the result matrix. It could be a 0, a 2, a 1, which is the correct answer, or a -1, all over the map, depending on what order you add those 4 numbers in. That's just one number of one matrix multiply, and yet we trust 64-bit arithmetic to give us just perfectly fine answers on large matrix calculations. So can we fix the IEEE 754 standard? Can it be rescued? Can we get help from the father of IEEE 754 himself, Professor Bill Kahn of Berkeley? Probably not. We've been trying for decades. He asserts that linguistically legislated exact reproducibility is unenforceable, and faster matrix multiplication is usually too valuable to forego for unneeded exact reproducibility. That's from How Java's Floating Point Hurts Everyone Everywhere, because Java's portability he didn't think was as important as just going fast. So if you can't get the old standard to change, you form a new alternative standard. I love this quote from Arthur C. Clarke. If an elderly but distinguished scientist says that something is possible, he is almost certainly right. But if he says that it is impossible, he is very probably wrong. I did a funny thing here. Here's another quote from Kahn saying, if we insisted upon perfection and found it, a machine whose every arithmetic function rounds correctly to within half an ULP unit in the last place is feasible for algebraic functions, but impractical for exponential and transcendental functions. I've written some papers showing that it's not impractical at all. And in fact, you can do it with perfect rounding and go faster than either GCC math library or the MKL math library. I did a web search for Gustafson mean. I was actually looking for something from Grumpy Old Man, but to my surprise, the first thing that came up was this. Anyway, I used this in a debate with William Kahn. That happened just before, well, it was the middle of 2016, because I was getting well known as an opponent of keeping IEEE floating point around forever without revising it. It's high time for something better. So he challenged me to a debate. We had some fun. Principles for next generation arithmetic. What should we set down as what do we want if we're starting with a blank slate right now? No covert use of extra precision. If you ask for a 64-bit number, you don't get secret help by having it go to 80 or 128-bit unless you ask it to. It has to be absolutely visible whenever you change precisions. If you fuse an operation, that means you defer rounding, like you do a multiply and an add and then round, as opposed to multiply, round, add, round. That only happens if it's explicitly requested. It cannot be done automatically by the compiler or anything else, or by the hardware. Math libraries should get correctly rounded answers for all inputs, not just most of them. This can be done, and it's practical. It needs support for exact sums and exact dot products, in other words, associativity. That has to be made available, and it's possible. It's not that hard to do. There should be no hidden processor flags or modes. As soon as you have a mode, then there's ways that your program can behave differently that are completely invisible in the code itself. The code and the data should suffice to tell you what a program is going to do. You shouldn't have to look under the hood to see what things are set to. Not a real, and I say that instead of not a number, because you could have like square root of -1, and that's a number, but it's not a real number. So I say not a real should be fast, quiet, and the last line of defense against exceptions, that is making mistakes like dividing by 0. If you try to do something like take the square root of a negative number or divide by 0, the first thing that catches you is generally the language that you're operating in. The POSIX standard will catch it and will produce an error message. That's after you've debugged the code yourself as best you possibly can. It almost never should fall through to the hardware to babysit your calculation and tell you when something's going wrong. You should map monotonically to 2's complement signed integer format, not sign magnitude format, which is really out of date. Do not underflow to 0 or overflow to infinity. This is something that Donald Knuth also rails on. You should saturate the signed minimum real you have or the signed maximum real that you can represent. That way you avoid an infinitely large relative error. So, breakthrough. Let me tell you a story. In November 14th, Supercomputing 2017, Kurt Cavill approached me and asked for a new number design for RISC-V. And, well, I knew I had these things called universal numbers. That's what the debate with Kahn was about. And the type 1 is variable size, so they're very hard to index into, and you need heap management. So, yeah, that's not hardware friendly. Type 2 unims are fixed size, but they depend on table lookup, so you're kind of limited to low precision, no more than 20 bits. That's not good enough. So I sweated bullets for a couple of weeks, and I had my eureka moment on December 3rd, 2016. I invented something. I thought I'd call it a guess, but I knew that now Kahn thinks guessing is a pejorative, so I'll call it something more positive. I decided to call them a posit, which is a statement that is made on the assumption that it will prove to be true. It's an optimistic guess. So posit arithmetic was introduced February 2nd, Groundhog Day, at Stanford. I was invited to give a Stanford seminar, and I said, I've got just the topic for you. It was that EE 380 seminar. They're put on YouTube, and they usually get about 300 views. Donald Knuth did give one and got over 1,000 views. Well, this talk has 23,605 views at the time I made up the slide, and it's still rising. There's still hundreds of people watching this thing because it's almost the definition of the new format. Near the end, by the way, Dr. Isaac Yonemoto did a live demo of successful machine learning with 8-bit posits. He did it on the spot, trained them, he trained a network, and then used it. Posits have just one exception value, not a real. It has only one way to represent 0, and it has only one rounding mode. You'll see what this does to the standard compared to the IEEE standard, to have all these simplifications. And I don't expect you to look at the formula here. By the way, I will leave the slides with Kurt, so anyone who wants to have a copy of these slides will be able to get them. So I know I'm going kind of fast here. This is the POSIT standard. It was ratified in March 2022. Theo was a help with that, by the way. I think he's in the audience. And it's 1/8 the size of the IEEE standard format definition. Their standard is actually like almost 100 pages long. And unlike IEEE standard 754, it's free. And you can download it at posithub.org. No restrictions of any kind. MIT open source license. It's pretty concise. The revolution is underway. So since that Stanford talk, people started jumping on and designing initially FPGAs, but now it's actually proceeding into native VLSI, where you can choose between floats and posits, or you can have both of them around at the same time. Here's some of the projects that are going on. If you go to Wikipedia and look up UNIM number format, there is a big table of about 30 projects all around the world and what state they're in to use posits. So this is not just a crazy idea that I came up with recently. This is a movement that is underway, and a lot of interest is for AI. So what reals should we seek to represent? I'm going to tell you some of the design motives that go behind posits. As I say, it's very rare to use values outside about 10 to the minus 13th to 10 to the 13th. And it's actually typical for it to be skewed a little bit. It's not a symmetrical 10. It's kind of tends to favor small numbers. So here's what you get with IEEE floats as they go from their smallest to their largest. How does the accuracy change? Well, on the left, that ramp you see is denormal numbers, subnormal numbers, they used to be called. And that's where the accuracy drops down to almost nothing. But this is a really bad use of exponent bits. In the early days, exponents were easier to build than fractions because fractions have to be multiplied and you have to build a big multiplier. But all you ever do with exponents is add them and shift them. So they made the exponent larger than it should have been. We don't really need flat accuracy over a huge range. If a number is huge, you don't care what its exact value is. You know, we say we're 4.3 light years from Alpha Centauri. You don't need that to 4 decimal places or much less 8. So posits have a ramp-shaped, tent-shaped accuracy profile. The bigger it gets, the fewer bits are in the fraction part. So your significance slowly drops. But in the sweet spot in the center where you do most of your computations, you have, let's say in this example, 4 bits more accuracy. And that's only one advantage of posits over floats. So they can map to signed integer format. If you put all the integers on a circle, where you start at the bottom of the circle at 0, you count up to 15 in binary. And right there at 15, it flips over to -16, because that's how 2's complement works. And then starts counting back up to 0. So posits map monotonically to that. And the cool thing about them is that you can change precision simply by adding 0 bits on the right or rounding off bits on the right. You don't have to decode the exponent, the fraction, anything. It's just like making a decimal a different size. And that's what we do with integers all the time. We don't think anything of changing from a 16-bit integer to a 32-bit integer. It's almost cost-free, right? We do that in C all the time. And it should be almost free. So you get better accuracy with fewer bits and bitwise repeatability and portability across systems. The POSIT standard took 5 years to get it absolutely airtight with all the mathematicians working on it. But if you follow the rules of the standard, you will get the same answer every time, even on parallel systems. It's a clean mathematical design. I hope that's apparent just from this diagram. 32-bit posits can often replace 64-bit floats. 16-bit posits can often replace 32-bit floats. And in neural networks, we've seen that 8-bit posits can often replace 16-bit floats. So that's energy, power, storage, bandwidth, and programming costs. Because if you always get the same answer, that really helps out the programmer. So you get deferred rounding of dot products using something called the quire. I won't go into that here because of lack of time, but dot products can stay exact even if they're a billion entries long, that is a billion terms. You get associativity of addition, and you don't have to constantly worry about, compensated summation and tricks like that. It just is exact because it's a fixed point register that's adding all these posit numbers. If you just take the bit patterns of a 16-bit number and go from 0 up to 32,000, 32K, this is how the precisions look. For B float has not even 3 decimals of accuracy. IEEE standard has about 3.5. Posits for most of it have a little over 4. But fixed point is 16-bit number. Wow, that beats everything. And some people are tempted by that. Why fuss with all that exponent stuff when you could just have even higher relative accuracy as a function of the bit string value? Well, the reason is application magnitude distributions are almost always 10-shaped. The closer you are to 0, the more accuracy you need. But fixed point is exactly upside down. It has the least accuracy near 0 and the most accuracy farther away from 0. Backwards of what you need. That really was why floating point was invented in the first place. So we found that 8-bit posits can train MNIST on LENet, for example. The gold standard of a float 32 gets 98.7% accuracy. We tried it with POSIT 8, and we got 97% accuracy. Even better if we used a little bit of a bias, 97.76. The float 8 has been proposed with 4-bit and 5-bit exponents. Neither one of them can do nearly as well as posits can. I like to point out to people that if you have a float 8 and it comes in 2 sizes, one with a 4-bit exponent and one with a 5-bit exponent, you do not have an 8-bit format. You have a 9-bit format. 1 bit has to tell you which type to use. And you can do a lot better with 9 bits with a good plan than just to have 2 different kinds of float 8. So we did some neural net experiments, not just on MNIST, but on some more substantial, challenging neural nets. Here's the gold standard on the top row, you see. And we tried Google's bfloat. It occasionally does really, really poorly. IEEE standard is even worse than bfloat. That's actually the worst format we tried that was in 16-bit. IBM has something called a dfloat, a DL float. And if you put a 6-bit exponent on IEEE, it actually does quite well. No one's apparently explored the whole range of exponents to use and figure what's the right size. If you go up to 7 bits of exponent, though, it starts to fall apart again because of quantization error, as they call it. There's the DL float right there. That's the one from IBM. The POSIT standard does uniformly quite well. And in fact, it even exceeds the accuracy of the 32-bit data set sometimes. So I'm hoping that people who are working on neural networks do take a look at posits. Here's something called generative adversarial networks. They're really cool. If you've ever seen these things that can take a photo of your face and make it look like Picasso painted it, that's a generative adversarial network. The top row shows how they can up-level a blurred image and make it sharp. There's one that can take a picture, identify the horses, and turn them into zebras. And here's one called DCGAN that's kind of an industry benchmark. It comes up with a fictional bedroom set. Just invent a bedroom set that's plausible. And you can see 32-bit does just fine. Floating point 16, that's rather strange stripes on the zebra, but otherwise it's okay. Here's a Posit with only eight bits, and it gets the stripes great. And it also does a very good job on the Monarch, getting the resolution high. And I think all but maybe one of the bedroom sets looks like a plausible bedroom set. You try it with FP8, whether 4 bits or 5, and you get garbage. It just doesn't work. I mean, the zebra looks sort of okay, but it turned everything into a zebra. It turned the dirt into a zebra. It turned the mountains into a zebra. Anyway, so here's a comparison of results. And sometimes lower is better, sometimes higher is better. I just tried to color code it with blue is good and red is bad to indicate where the merits are. But it does appear that for generative adversarial networks, 8-bit posits are going to do just fine. When you get as low as 8 bits, you can build different kinds of circuits. You can start to do really quick integer maps that don't require building a multiplier, let's say. Here's something that Oxford did with 16-bit posits. They tried them on weather modeling and also climate modeling, and found them to be considerably better than floats. In fact, this is so much better. I don't really have an explanation for it. I don't know why it's so much better, but they've been publishing papers about this for years now. Here's an independent test by Lawrence Livermore National Lab that was done by Peter Lindstrom. And I think I have an animation I hope will play correctly. It's shockwave goes around a corner. As it goes through the L, you can see it produces areas of negative pressure. And this is where, of course, all the rounding error comes from. Really nasty gradients there that make the computation of the derivatives not that accurate. And what they found, just in summary, are that posits are 2 orders of magnitude more accurate than floats. The 64-bit format's down here. You want, of course, lower is better because this is error on the y-axis. But posits did better than floats. So the worst thing, they tried a lot of different things that they've invented at Lawrence Livermore, and the best thing they found was the posit. So 32-bit precision may suffice now. This is a really early computer, but there are a lot of them in the 1950s. They all had 6-bit bytes, 6 bytes per word, and so it was a 36-bit word. And if you make a floating point out of that, you actually get, I think, you get like 28 bits of significance. But when the IBM 360 came out and took over the whole computer industry, they had to cut back to 32-bit because they wanted powers of 2. So as to be able to index into arrays just by shifting. It just wasn't quite enough. You now had 24 bits for the significand. And what if you could somehow get back up to 28 bits again and then go back to using these numbers for structural analysis, circuit simulation, computational chemistry? Computational chemistry is probably the hardest one. It probably does need 64-bit, but I believe that for circuit simulation and structural analysis and a lot of finite element modeling, we should be able to replace 64-bit entirely with 32-bit posits. So that's a 2x effect. That's like a turn of Moore's law. We used to have to wait 2 years for these 2x improvements, and now they've stalled. But that's actually probably more than 2 times, because when you make numbers thinner, less bits, it's not just a relaxation of the bandwidth. It means that they fit into let's say they used to fit into L2 cache, but now they fit into L1 cache. Or they used to have to be out in main memory, but now they actually fit largely in L3 cache, something like that. So in summary, these things give you better answers and fewer bits. I'm not saying that this is the end of the revolution. It's just, I think the latest step is at least try posit arithmetic. We'll find better things as we go along. But we can have bitwise reproducibility for real number programs. It's achievable for the first time. We don't have to just shrug our shoulders and say it's too hard, it's impossible, it's impractical. Low precision posits work really well for AI apps. And posit adoption has caught fire, especially on RISC-V. So Kurt, this is a full circle. You started it, and now here I am talking. I'm really pleased to be able to do this. Posits can allow smaller precisions to achieve acceptable accuracy, making posit arithmetic cheaper, faster, more power and energy efficient, and smaller chip area. So thank you. For more information, go to posithub.org.